Order! Order! You are an incorrigible delinquent at times. Behave yourself, man!
Now, the sound ripples detected in the fabric of space-time have elicited something more akin to a huge cosmic scream from the scientists that discovered them. Of that ilk, all credit must go to Einstein, who first predicted gravitational waves a century ago. But today, in an announcement that electrified the world, astronomers finally detected the waves and conceded he'd been right. The skies, one said, will never be the same again. So what does this mean, and what does it change? Rebecca Morell reports.
It's him again, making waves in the world of physics. This is the equation behind Albert Einstein's theory of general relativity, conceived 100 years ago. A pillar of modern physics, it told us everything, from the motion of the planets to the presence of black holes. But it also proposed the existence of something else. Our universe is a gobsmacking sight, but one of its most intriguing features is its gravitational waves. It's awash with them, but we've never been able to see them until now.
We have detected gravitational waves. We did it.
The news today that we've finally found them is quite literally astronomical. Almost certainly Nobel Prizes will be given out for what some are already calling the discovery of the century. So what are these waves? The idea is that as any object moves through the fabric of the universe, it gives off waves of gravitational energy, much like the ripples that emanate across the surface of the water as you throw a stone into a pond. Everything on the move, including you and me, emits them. But in universal terms, we're pretty puny, so our waves are incredibly weak. When it comes to cosmic giants, though, like exploding stars, well, these generate tsunamis of gravitational energy. So a good opportunity for scientists to finally detect them. But what is it they've seen? As gravitational waves move through the universe, they eventually reach the Earth. And when they do, they gently warp anything and everything they pass through, stretching and squeezing atoms, but by a tiny, tiny amount. And it's this minute disturbance that scientists have detected, emanating from this explosive event that took place 1.3 billion light years away. Two black holes moving ever closer together. Eventually, they smashed into one another, merging. The collision generated a surge of gravitational ripples that reached Earth, just in time for the switching on of an experiment designed to find them. So why should anyone care about a few ghostly oscillations? Aside from providing another feather in Einstein's cap, who's been proved right once again, it heralds in a new era in astronomy. Until now, even our most advanced telescopes could share only a fraction of the cosmos with us. The rest was dark, unseen. Now we can detect gravitational waves, we'll be able to learn more about the events that generated them, looking deeper into space and further back in time than ever before, perhaps all the way to the Big Bang. It really does give us a brand new perspective of the universe.
Rebecca Morell there. Well, Professor Sheila Rowan, Director of the Institute for Gravitational Research in Glasgow, is one of the researchers involved in the project, and I can't imagine what your day has been like, Professor Rowan, but give us this sense of the history. Einstein was right, and he knew this 100 years ago. How has that gap taken so long, if you like, to fill in?
It's a fascinating story, and one in which people actually have written books about the history of the field because it's so interesting. Einstein made this prediction, as you say, 100 years ago, but for decades, actually, it remained a kind of mathematical curiosity. People weren't sure that this prediction of gravitational waves had any real physical meaning, that it was an effect we could detect. And it took until the 1960s before people thought that this was maybe something that was real, that we could actually try and detect, try and sense, and they've taken the following decades in between to get to the point that we are now.
And one scientist put it that the sound of space has changed. I mean, through that sound now, do
Yes.
we get the history of the Big Bang? Do you buy that?
Not yet, but that's a goal for us in future. What we've started to be able to do is to listen to the gravitational history of our universe. We've started to hear sounds from our local universe, from black holes, as we heard today, spiralling in to collide. And so far, we can listen to those within a certain volume of our local universe. What we'd like to do is make our detectors even more sensitive to sense further out into the universe. The further out we go, the further back in time we can sense. And eventually, if we can make our detectors sensitive enough, we'd like to reach back to gravitational signals, potentially coming from the Big Bang.
God, it's extraordinary that. Does this tie in with Einstein's theory of relativity? Does it make sense of that? Does it prove it?
Today's result is a fantastic confirmation of Einstein's theory of general relativity. Everything we detected today fits with general relativity, and that is in some ways fabulous. It's a fabulous confirmation of Einstein's prediction. But we know that general relativity, being a fabulous theory, it still doesn't tell us everything, the full story of all the forces that govern our universe. So in some ways it's fabulous. It's a fabulous confirmation of general relativity, but still there are boundaries to push.
So does it disturb things that scientists had thought were set in stone? I mean, has it created more problems for you when you step back?
I don't think it's created more problems for us. It's given us a new tool, a tool that we really didn't have before, to study, as we heard, the dark side of our universe, because pretty much everything we know so far we've got by going out and turning our telescopes up, sensing the light that we can see.
So it's all been done with light and all been done visually?
Light and all its different spectrums, so X-rays, gamma rays, they're all part of the spectrum of light.
What does this do to gravity and to our understanding of gravity now, which has always been the most sort of mysterious force, if I can call it that?
It gives us a new tool to try and understand where our limits of Einstein's theory stop. Because for the very first time, we've got objects that have the strongest gravity that we can think of. Black holes, of course, are called black because not even light can escape them. And two black holes merging, colliding, as we saw today, is gravity in its strongest form. And we've just started to be able to see what's happening in those limits of the strongest gravity we can think of. We got our first signal today, just our first hint that we heard about. But to study those systems, it will push our understanding of general relativity to the limits and test really what we know.
Professor Owen, great to have you in. Thank you very much indeed.
I've been getting away with it all